I have a ton of content that I'm going to try to jam into this session, and I'm going to move really fast. I apologize for that. There's a good chance that we will run out of time for Q&A, so I will leave cards. You can track me down online or at the party or tomorrow or whatever. I'd be happy to talk about any of these items in more detail. There's a bunch of great security sessions. Some of them have already passed. There's one more coming up after this. I would suggest checking those out as well. So in the security and cryptography space, I kind of realized as I started putting material together, there's a ton of jargon, a ton of terminology that's very sort of foreign, unknown, or maybe even scary to people in this space. And we're actually going to cover almost all of these topics in the next hour. So hopefully you come away with some new words that you can use to impress your friends, and maybe you even know something about what they mean. So we're going to start right in with challenge response. So when the internet started out, the earliest protocols, when they needed to authenticate users against a server, that was done with what we called a plain text password. It was a real simple setup. Alice would send a message across the wire. Hey, it's me, Alice. The password's Penguin. And hopefully nobody overheard that. Server would let them in, right? The problem is Mr. Evil, he's down here. He's listening in, and he's now got a copy of Alice's password, right? So it didn't take long before this guy showed up, and we've kind of been trying to combat him ever since. So the first step that we can do is approach this problem a little differently. And so I'm kind of showing a very rudimentary example of challenge response. So in this case, we've got a prearranged secret between these two parties, 4718, might be a password, PIN code, or something like that. And the way challenge response works is that Alice introduces herself, provides her username, and the server comes up with random numbers. This is actually the challenge that's returned to Alice. If it's really you, then divide our secret into this number I just came up with, right? So Alice can do that. She knows how to do division. So she takes this big random number, and she knows the secret, she does the math, and she's got a remainder, and she returns part of the answer to this math problem. So she says, I did the math, the remainder is 360. The server can do that same math and come up with the same remainder. So now something special has happened. This guy is foiled, right? Because Alice was able to prove her identity without actually revealing the secret. And the server can have some confidence that that's who we really expected to be logging in. Now this is a really simplified example. In reality, this isn't a very strong system because even though she didn't share the password itself, she did kind of give a lot of clues about what the password is. She eliminated a lot of potential passwords out of the potential realm. So an ideal design for a challenge response system would reveal as little information about the secret as possible and provide an extremely high degree of confidence to the server that Alice knows the secret. And it's not someone just randomly, accidentally coming up with the right answer to the challenge. All right. So we're going to move on to the next topic, hashing. There's actually a bunch of terminology and technologies that are all kind of in a similar space. So in a really simple case, you might think of even like a checksum or something like that in this space. Another common term that's kind of interchangeable with hashing would be digest or fingerprint. Those are all kind of interchangeable depending on the vendor you're talking to. And the general idea with a function in this space is that it's a mathematical function that takes a variable length input and returns a predictable result that is always a fixed length. And usually the input is longer than the output, but it doesn't have to be. So let's look at LUN check. A lot of you have probably seen this before. If you have a form where you're having people type in a credit card number and you want to make sure they didn't miskey a digit, in this case, Visa number, you probably all have one of these in your wallet. The account number, it looks like it's 16 digits, but it's actually a 15-digit number. And then the LUN function produces a check digit, which can be used to verify that you didn't miskey the number. Now, it's not a perfect system. 10% of the time, you might miskey the number without the system detecting it. But it does help to catch some situation. This is also used on like your UPC barcodes at the checkout to help prevent smudged codes from accidentally being scanned as the wrong item, things like that. If we look at another example, we could see a different account number produces a different check digit. Now, because there's only 10 digits available in the output of this function, sooner or later, we're going to run into another account number that produces the same check digit. And there's a key term for this in cryptography. We call that a collision. And that's really sort of a very important concept with a lot of implication. And the other thing to keep in mind, because the space is so small of the output, it's not very hard to reverse engineer this system and come up with other intentionally come up with collisions. Like it doesn't take me more than about 10 tries to make up a credit card number that will pass one check, right? 10 tries at most. And then the other thing to keep in mind is different lengths, like Amex uses a shorter account number, but they can still use the same algorithm. All right, so there are a lot of hash functions out there. The LUN check is really only intended for detecting errors, but the first hash function that I'm aware of that was built with the intention of sort of obscuring information about the input, similar to that challenge response idea. We want to reveal as little information about the input as possible, was MD4. Right away, they realized that there were some problems in the design, so it never really made it far before MD5 came out. And that's still widely used today, but it's actually been compromised. It's not strong enough for security uses anymore. It could still be used for error checking or for other types of use cases, but you wouldn't want to use that in a security situation. The industry standards today are going to be based on SHA-2, which actually supports multiple lengths of output. So that we usually just call it SHA-256 or SHA-512. Those are just different modes for SHA-2. All right, so let's switch gears and talk about user tables. This is something that you should generally just try to avoid as long as possible because handling passwords is a liability. There will be long debates about having user tables, and those arguments are often very sound, but sooner or later it may become a business requirement. Even if it's not for tracking your own employees, you might need to track information for your customers or something like that. But there are a lot of bad things that could happen if this file ever got out. If you had a rogue employee or someone broke into your building and stole your server and they've somehow got a copy of this table, obviously the most immediate concern is that they could access your company information using your credentials. That's a problem, especially because the CEO, user number one, his password is football. The other thing that would be of great concern to me is that CEOs are not very original in their use of passwords. And so he probably uses that same account for his stock trading and his financial banking login. So even if you've reset all the passwords in your company, Mr. Evil can take this information and go try logging into a bunch of banks until he accesses that information, right? So people that reuse passwords create problems for us. And then even if you never have a breach and your user table never gets out, if one of your employees is experiencing check fraud or identity theft, and they sort of think back, I just realized that I'm using the same password for my credit union and for my company login, and Fred, the IT guy, just asked me what password I wanted, and I wrote on that sticky note, I wonder if Fred is the guy who's emptying my checking account. So any way that you can avoid ever touching the password just removes all doubt about you, which is a good place to be. So one thing that we could do if we do have to store users and secrets about them would be to use a hash function. So this is just a look at the same table if we replace the password field with a hash field. And the whole point of SHA-256 is to not reveal any information about the input, while at the same time sort of being able to guarantee that we could reproduce the hash later. So when S. Johnson comes to log in later, he could provide his password football, we'd run the hash, and if it's a match, we know it's him. We know that he has the password that's needed, but we aren't actually storing the password. So this seems like a good step in the right direction. So let's jump out to a demo. So this is sort of that slide we were just looking at. We've got a list of users, and we've got passwords there. Maybe you're doing something nice like obscuring their password when they actually have an interface, but you're still storing it in plain text in the table, right? I see this in a lot of systems. So if we upgraded that to something like a hash, the interface to the user could be the same. And we see that I just changed the password to football, and I can't see football here. There's no way to use math to get from that hash back to the word football. But there's already a problem I'm spotted here. It looks like user ID 1 and user ID 8 have the same password. Now, maybe I don't know what the password is, but if I could convince one of these guys to give me their password, like if I threaten to, I don't know, throw a water balloon at them or something, and they give up their password, now I could use that to get into the other account. So there's a problem there, but there's a much more serious problem. So as I was putting together the sample, I did a little Google search or two, sort of saying, hey, what are some of the most common bad passwords? And one of the top hits that came up was a publicly available download of 10 million most commonly used passwords and usernames. And it's out there. I'm not going to put it on the FileMaker site, but you can find it without looking hard. And so I've just narrowed that down to the 10,000 most common. And so that looks something like this. These are all passwords that you've probably seen your users trying to use before. Obviously, these are not very creative or hard to imagine that people would do this. Now, the next step that we might do is we might build an automated system that just takes these 10,000 passwords and just repeatedly tries to log into the server until we find somebody's account that we can log in. And that would be what we call a dictionary attack. It's great news that FileMaker 17 actually helps to prevent dictionary attacks. FileMaker Server 17 now has a lockout feature. So if someone is doing a dictionary attack against your FileMaker server, they are going to be abruptly stopped after 5 attempts. And they can retry again later, but it's going to really put the brakes on their ability to mount a real dictionary attack. Yep. You'll have to ask an engineer about that. I would recommend, if it matters to you, you should test it, because it's not very hard to test. All right, so let's assume that we're not doing a dictionary attack, but we convinced some employee, we paid him with ice cream or something, and he downloaded a copy of the user table and gave it to us. And so now I'm going to take my table of passwords here, and I'm just going to add 4 calculation fields, and I'm going to compute the hash for all of these passwords in a stored field, which then I can index, right? It turns out that for 10,000 passwords, computing all 4 of these hashes took about 4 seconds on my computer. So if you interpolate that up to the 10 million password file, you're looking at like maybe a minute to generate all the hashes for all 10 million passwords. And then that would look something like this. When you produce a file like this, we call this a rainbow table. All right, so you can probably think ahead to what I'm about to do. I'm going to go to my demo file, and I'm going to add a reference to the rainbow table. And I'm going to just go ahead and make a relationship from my SHA-256 stored hashes to the rainbow table. And then on this layout, I'll go ahead and add a field and I'm going to look across and grab the password. All right, it takes a second to build the index for all those 10,000 records. And even though we have not mathematically reverse engineered the hashes, we've worked forward from a whole bunch of passwords that people are likely to use, and we've matched that against like over half of the users in our system because their passwords weren't unique or original enough. So what can we do about this? Sort of the next evolution of protecting passwords is to use something called SALT. So basically the idea of SALT is to, every time that somebody changed their password, you generate a random number or random string of text. In this case, I'm doing like 6 or 8 digits from a hex code here. And you can just take that random string, concatenate it with the password they provide, hash that, and store it. And then we need to hang on to that SALT. So in the table, we're actually going to store the SALT that we came up with, and we're going to store the password. So every time we change the password, even if we set it back to the same password that it was before, we're going to regenerate the SALT every time. So every record has a different SALT, and we can verify using sort of repeating the process in the other direction. If somebody wants to log in, we can provide the password. We take the SALT, combine it with the one they provided, run the hash. If it's a match, they're good, right? So login successful. So right away, this helps to prevent that first situation where we could see just sort of with our plain eye that 2 users were using the same password. It avoids that situation. And it does mean that I can't just make a direct relationship from my rainbow table to these hashes, because all the hashes in the rainbow table don't match this. But if I'm going to target the CEO and I find his username in this table, I'm just going to take the SALT that's used for storing his password, and I'm going to go recalculate the hashes for my 10 million most common passwords with that SALT added to the formula, and now I'll have a rainbow table that I can use to try to attack his specific hash. So I've put up some speed bumps maybe to the process, and if I was going to automate this, maybe it's taking me a minute for each account that I want to try to compromise to see if they have a weak password. So I don't mean to freak everybody out, but this is a problem. I think the number one recommendation I would use would be to use a password manager, like iCloud Keychain or LastPass, 1Password, any of those. They're going to provide unique, distinct, original passwords, which will not be in the list of the 10 million most common passwords. And if you can provide training to your users that says that they should use products like that, that's going to be a big win for them and for you. Yeah, I think that's the best thing you can do. There's all kinds of ideas about password length or require a special character, but then you just have like football 1, football 2, football 3. Like sooner or later, those passwords are also going to be in the list of the 10 million most common, and you're still going to be at risk of situations like this. The other thing to do is just protect the file, right? You can make sure your physical security is good, make sure employees that shouldn't have access to this information don't have access, things like that. Next up is encryption. So each of these topics get a little bit more advanced. So symmetric key cryptography is what we're going to talk about first. Sometimes this is also secret key crypto, same thing. This is a fairly simple scheme. It's been around for a very long time. And the general idea is that you come up with a key or a random number, and you share that among your circle of trust. So you've got Alice creates this key, and she wants to be able to communicate securely with Bob, maybe one other person, something like that. She could share this key with them. The hardest part of this process is making sure that Alice, gets the key to Bob without someone else being able to get a copy of the key. Distributing the keys is one of the biggest problems with cryptography. If you can get past that, a lot of other things work really well. All right. So the easiest way to show this is just with a demo. So we're just going to jump back over here. So the classic training example for symmetric cryptography is the Caesar cipher. So we've got this message on the left, and we want to encrypt it. Can somebody give me a random secret key between 1 and 25? 24. That's a good one. I don't think anybody else has that one. All right, so we can run the Caesar cipher on this text, and we can see this message is encrypted. On the other side, we can pass that to the clubhouse down the street. They use their secret decoder ring to get the original message back, decrypt it, back to the original. So the Caesar cipher, if you haven't seen it before, is just shifting the letter T 1 digit. In the case of 24, we went all the way around the alphabet, so it's almost like -1 to get from T to R. The problem with Caesar cipher, well, there's numerous problems, but one is that the size of the key is really small. It would only take me at most 25 tries of trying different keys until I get an intelligible message out, and then I've guessed the key, and I can decode every message from that point forward. If I don't want to do a brute force attack against the key, I could do what's called cryptanalysis against the ciphertext. So I could start looking at this text and see if I see any patterns in here that are interesting. So I'm assuming that the people I'm trying to crack their message speak English, and the most common word in the English language is the. I happen to see a phrase that's repeated here, RFC, RFC. I bet that's the word the. I can do a little arithmetic, make a very educated guess on what the key likely is, and so maybe it only takes 1 try to come up with the key to break the message, right? So ROT13 is just a specific use case of this. So if we take this up to modern day encryption, the setup looks the same. It pretty much is the same. The key difference here is that we're going to use AES, which is industry standard encryption right now. We've got the same kind of message. And we can have a much larger key, and in fact, with this implementation, we can type as long a phrase or paragraph as we want. So maybe our secret is this is a test, and we can encrypt. So just to the plain eye, we can see that there's something a lot more complicated going on here. The ciphertext is going to be hard to do cryptanalysis on without a degree in mathematics or something. Even then, the brightest minds have worked to come up with an algorithm that is nearly, well, as far as we know, impossible to reverse engineer. So in this situation, based on what we know now, the best way to compromise this ciphertext is through brute force attacks on the secret. So you would just try all kinds of phrases until you get one that works. Now, in FileMaker, we can decrypt the text again if we know the secret. If we don't know the secret, if we just take a guess and we try to decrypt, the function just returns the question mark. That's the output that FileMaker produces. So how might you use this in a practical situation? Maybe you have a customer table and you need to store some sensitive information about your customers. Maybe it's not their password, but your customers tell you things about themselves that and you tell them that you'll safeguard their information. So you could have a container field on your customer record with encrypted data using the same function we just saw on the last screen. And then you might have a limited number of employees that you tell the secret to. And you could say, hey, whenever you need to work on Superman's customer record, you're going to need to know this password. Now, for the demo, I just put the password right here on the layout. I'm sure you guys wouldn't do that. It would be like a sticky note on the screen or something. So if I mistype the password, we've got a script that detects that and says, sorry, that's not the right passphrase. If we do it correctly, whoop. I hope this is the right password. Okay, got it right this time. All right, so I just decoded the data. I happen to use JSON inside of the encrypted payload. So I just kind of broke out that information, put it in a dialog box. Maybe the employee can update this information now, change something, and when they save, I just use the crypt function to put it back into the encrypted container. So I'm sure you can think of a lot more creative uses, but that's sort of the crux of the idea of how you might use the AES crypt ability to protect data in a specific field. So we were just using the crypt encrypt and crypt decrypt function. I was hoping to step through those scripts, but for sake of time, we're just gonna keep going. But feel free to download the sample file and exploit it and use it however you like. So of the symmetric cryptography systems out there, we just looked at Caesar. DES is probably one of the most widespread used algorithms out there. It came out in the mid-70s. When they realized that it was probably going to be able to be cracked, they thought, hey, I've got a great idea. Let's just run our information through the encryption formula 3 times. That'll make it 3 times as strong. It turns out that wasn't really true. So it was a nice idea. It didn't work out. It was compromised in 2016, even in the triple DES form. But there still are a lot of routers, VPNs, appliances that are still using DES or triple DES. And you should really get rid of those if you can. So AES is the one at the bottom. That's the one that the NSA requires for handling any sort of documents classified secret at 128 bits, and then at a higher bit size for anything classified top secret. If they're mandating that all of their employees and contractors use it, it's probably good enough for the stuff I'm doing. Maybe. Maybe. There is a performance penalty a little bit based on key size. We don't really get a choice. I guess I'll just leave it at that. So in FileMaker, the encrypt and decrypt functions in FileMaker 16, we don't get to set the bit size. It's set at 128 bit. Encryption at rest is actually using the higher bit size. So that's been around for a while. So you've got the option to encrypt the entire file at this really high strength. Or if you want to do like a single field, you could use the functions at the 128 bit. All right, so let's move on. What's different about asymmetric cryptography compared to symmetric cryptography? So if you think of like folding the paper to check for symmetry, in the symmetric scheme, both parties have the same key. In asymmetric crypto, the keys are different. All right, so Alice comes up with a random number, and this is usually like a couple of large prime numbers, things like that, and she builds a private key and then uses a mathematical transform to produce a public key based on that same input. And there is very unique properties about these private and public key. The public key can't be used to get back to the private key. So this is one of the hardest concepts to kind of grapple with, I think, if you're new to this topic. There's kind of some related functions to this that are called trapdoor functions. And the illustration that's typically used is like a padlock. So you might have a vendor or someone that's doing work on your property, and you tell them like, hey, here's a padlock. You open the padlock, you hand it to them. When you're done, would you put the tools in the shed and lock it up? Right, so the vendor can finish their job, and they can put the padlock on the door and close the padlock. But once they've closed the padlock, they can't get the tools back out. Right? But for me, it's very easy to open the padlock. I have the key. So this is sort of the general principle of a trapdoor function that it's easy to go one direction. It's very easy to lock the lock, but it's going to take a lot of force to open the padlock or the key, right? So the public key, because you can't use it to get back to the private key, we don't have to worry about who gets a hold of the public key. In fact, some people have posted their public keys on billboards to prove this point. You don't have to worry about that. That can go, even Mr. Evil can have a copy of your public key. That's fine. The private key should go in your safe or somewhere very protected, and you should never, ever, ever share it with anyone. If someone says, hey, I'll set that service up for you, just give me your private key, don't do it. So how does this work? When Bob wants to communicate a secret message to Alice, he takes the public key for Alice, and he takes his message, he encrypts it. That ciphertext then goes across the wire, and Alice takes her private key out of the safe, she decrypts the message, and she can read it. Now, Mr. Evil, he might have the public key or somebody else. They can intercept that message. There is no way for them to decrypt the ciphertext. Only the person with the private key can decrypt the message. Now, there's a unique property. We can kind of run this backwards. Alice might take a message and encrypt it with her private key. And that doesn't really do much to protect privacy because everyone has the public key. Anybody could decrypt it, right? However, when someone decrypts a message using Alice's public key, they can be completely confident that Alice produced the message. There's no way anyone else could have produced that ciphertext unless they were in possession of the private key. So that principle we call signing. So I wanted to do a demo, but they wouldn't give me like a 3-hour session. So here's how to do the demo. You can download the slides and do it later. But this is the command line steps to create a key pair, an RSA key pair, and then encrypt a message and decrypt a message. If you're on a Mac, these tools are already built in. If you're on Windows, they're open source, and OpenSSL is a standard security utility. You probably should just install it and try it out. So in asymmetric cryptography, all the ones I listed here don't have any known mathematical compromises. RSA is clearly the most widely used scheme. And there is some concern growing that small keys like 1024-bit could be breached with enough computing power with just brute force attacks of trying keys. So most people are moving up to 2048-bit RSA keys just because it would take so much longer to brute force. And then sort of the state of art that's being used by NSA, which is also public if you wanted to use it, is ECC. Which is based on elliptic curves, whereas RSA is based on hard math involving primes and factoring, which is pretty cool stuff. So this is not available directly in FileMaker as a function, but there are plugins that you could use if you needed to do this sort of thing in FileMaker. All right, so these are building blocks. We're going to take some of the things we just learned about and put them together. So HMAC is a combination of hash functions that we learned about and symmetric cryptography. So the idea with HMAC is that we want to achieve data integrity and authentication. So Alice can build a message, and she can send that over to her vendor, Bob, something like that. And they've previously securely exchanged these secret keys. And Alice can take that message and combine it with her secret key, maybe even just concatenate the message with her secret key, produce a hash. Now you can't get from the hash back to the secret key, so that's good. And you can send the hash along with the message, and then at the other end they can basically repeat the process to ensure that the document hasn't been compromised or modified, and also that someone within the circle of trust produced the signature, or the HMAC. So this exists in FileMaker. We'll jump out really quick and do a demo of that really quick. So a use case example might be an API where you want to do stock trading. And so I've got an order here to buy 4 units of Apple stock. and maybe our secret that's been mutually agreed on between me and the stock trading company is up here, and I'll go ahead and generate the hash for that. And then they basically repeat the process on the other end. They can read this message, this buy order. They can use the secret key to verify that it hasn't been modified. Now, if Mr. Evil intercepts this message and he tries to increase the buy just so that I run out of money or something like that, it's going to change the hash code. If you don't have the secret, you're going to get a different hash, things like that. This is available in FileMaker. So next up is almost like HMAC, digital signature. Instead of combining a hash with symmetric cryptography, digital signature combines it with asymmetric cryptography. And this provides the same first two principles, data integrity and authentication, but it also provides non-repudiation. So what does that mean? It means that nobody except Alice can sign the order to buy the stock. Now, why would this be any better than HMAC? It basically boils down to maybe your stock trading vendor, Bob, has a coworker, and this guy turns out to be Mr. Evil. The coworker has access to the secret key, and he can actually produce a stock trading order and sign it because he has access to this shared key. And there's no way to prove that Alice didn't make it because they're all sharing the same key. So non-repudiation is this idea that we can have confidence that Alice is the one making the order. And so depending on the type of API and situation you're in, different vendors, some of them will use digital signature, others will use HMAC. They're very similar, but they have slightly different properties, so that's the key difference. I'm going to skip this demo because I'm afraid I won't finish otherwise, but this is in the demo file. The function isn't available directly in FileMaker, but it's available through Base Elements or Monkey Bread. There probably are other plugins that might do it as well. All right, so this is sort of we're almost reaching the peak of the things that we can do based on what we've learned. So SSL is sort of the end game. This is what people are most often confronted with and trying to figure out how to make work. And this is a little different, but there's 3 parties involved in this system. And this started out and was most used for e-commerce, so shopping carts. People wanted to check out and provide their credit card number in a way that wasn't going to leak it. So this is going to go fairly deep. If you had trouble keeping up, I apologize, but you can download the slides and reference it later. So there's a setup process to make SSL a possibility. So let's look at that first. So we start out with these trusted entities. Maybe these are banks or well-known companies, things like that. We call them our certificate authorities. And they produce a key pair, an RSA key pair typically, and they sort of stamp their business card and they provide their public key. This whole thing is bundled together in a file that we call a certificate, and then they give that to some of our software vendors. So someone like Apple or Microsoft or Mozilla would collect these certificates from many different trusted certificate authorities and bundle those in their software. So when Bob installs his operating system, it's preloaded with a bunch of these certificates that we call those the trusted roots. The next step is Alice is getting her business set up, and she wants to set up a store online, or maybe she wants to set up a FileMaker server, and the first thing she does is to create a key pair, just like the certificate authority did. So she's got a private key and a public key, and she's never ever going to share her private key with anyone. The next thing she does is she produces what we call a certificate signing request. And this is basically kind of like her business card. It's information about her company. She's registered this domain name for her tube socks, weartubes.com, which is available if anybody wants to go get it. And then she takes her public key out, attaches that to the request, sends that to the certificate authority, and then traditionally, the certificate authorities didn't work for free, so you had to send some money, some compensation. And then the next thing that would happen would be the certificate authority would do some kind of verification or background check. Now, different authorities had different policies on how they did this. And there's actually different levels of background checks. Just like if you're doing a background check on a person, you can pay more for a stronger check. That still happens with certificates. And once they're sure that this is really a legitimate use of wheretubes.com and that Alice is the person who registered that, then they will use their private key to sign a file, and this payload we call the certificate, and that goes back to Alice. So they used the private key, but they didn't share it, right? And Alice never gave her private key to the certificate authority, only the public key that's actually bundled up in that certificate. All right, so she now configures her server. This would be like the FileMaker server, import private key, import certificate. You don't need to import the public key because that's actually bundled in the certificate. So that file that you might have stored away, you don't really need it once you've got the certificate. And we're good to go. So now we're ready to actually do some commerce or have someone log in to the website. So Bob is interested in these socks. He's heard that they look pretty cool. He starts out with a challenge. He says, hey, wheretubes.com, is that you? Prove it. So he sends this request off. Alice responds by sending back an entire copy of her certificate. Right? Now there's nothing secret about her certificate. She can give him the whole thing. It's got her public key in it. She certainly doesn't give out her private key. And she says, hey, you can message me using this public key. All right? Now, Bob wants to know if this is a forgery or the real thing. So he looks at this certificate and he sees that it's signed by Penny Secure Root. And he looks in his trusted roots. He finds a match. So there's a public key there, and he can use that to verify that this certificate hasn't been tampered with in any way and that it's legitimately signed by the certificate authority. So once this is done, now he's got a copy of Alice's public key because she sent it to him and he verified that it's legitimate. The next step in this process, Bob wants to do something that's more efficient than asymmetric cryptography. So he creates a new key. He rolls the dice, comes up with a big random number. This is going to be a symmetric key. We call this the session key, and it's going to be used just for the session. He takes Alice's public key. He encrypts the session key, sends it back to Alice. Okay? So he's basically saying, hey, for the rest of this session, we're going to use this secret, all right? And then he encodes that so nobody else could read that message. Alice is the one and only person that can read that message he just encrypted because she's the only one with the private key. She decrypts it, and now she's got a copy of the session key. And that's good. Everything worked. Alice sends back some kind of acknowledgement. Okay, I got it. She proves that she was able to decode the key by basically encrypting a message with a session key and sending it back. And life is good now. They can use this session key back and forth. Either of them can send messages with the session key. Nobody else can read those messages. Now, I kind of carefully worded this. So now we have a secure channel of communication between some guy, he says he's Bob, I don't know, and Alice. And we know who Alice is, right? But there's nothing that happened here that proves who Bob is. We've only proven who Alice is. So maybe Bob is your employee. Maybe Bob is using FileMaker Go on a jailbroken iPhone. Or maybe he's using it on Windows with some malware or something. So it's really important that you also solve that other problem. I'm not going to get into all that today, but this is sort of what happens to facilitate a shopping cart, and it's a lot of what happens in FileMaker too. All right. So most of the times I get calls about SSL, this is the problem right here. They have the orange lock, and they're trying to get the green lock. So let's look at some demos about why that would be happening. So let's say we're on a Windows client, and we open up hosts, and we'd like to get connected. We've got a favorite in there, and it's trying to connect to that. Now we can see that the name that's in the favorite is pretzel.3prong.com. That's the host name that the favorite says we want to connect to. But we're getting this warning because the identity doesn't match what's expected. Now you can click View Certificate, and you can see all kinds of details that are inside the certificate, including who it was issued to. So this certificate was issued to fmsdev.3prong. That doesn't match pretzel. So that's why we're getting the warning. You can see the subject in here. This is the same stuff that we were just kind of looking at the process. And even though the certificate appears to be okay according to the Windows check, the business card in the certificate doesn't match who we thought we were connecting to. And that's why we're getting this warning. Right? Let's look at another example that's real common. This is using Bonjour. So you're on the local network, and I'm actually going to pause this. So this name showed up here, and this is the name that you configured your server and said, this is what I want to be known by. It actually doesn't have anything to do with SSL. The name that Bonjour used when it announced itself on the network was one of these .local domain names. It turns out there is no way to buy a certificate from a certificate authority that ends in .local. It's prohibited. All the certificate authorities have agreed to never issue a .local certificate. The public ones, anyway. We can open up the certificate, and macOS looks a little different, but it's a lot of the same information. We can see that the certificate is installed correctly, and it's issued to fmsdev, but it doesn't match our .local domain name. So this is always going to have the orange lock. If you're trying to kind of piece together maybe what's going on, you can hover on the name to see what the Bonjour name is and why it doesn't work. Also, if you go ahead and just add it to the favorites. The key here is that that name at the top, that's the name that FileMaker is trying to match to the certificate. So if the name up there in host internet address is not the name that you used when you bought your certificate, you can't have a green lock. The favorite host name, that one below, you can type whatever you want in there. That's just the label for the favorite. And so I think, unfortunately, that also adds to the confusion sometimes. Now, just to prove that you can get a green lock, it is elusive, but it is out there. What I typically recommend for people is let's make a favorite. Let's type in the host name that we are quite sure that's what we want to connect to. That's also giving me the same host name that I used when I purchased my SSL certificate. I don't get any warnings here. That's good news. I get the green lock. If I want to interrogate the certificate and find out more about it, I can click on the lock and sort of see the breakdown of who signed it, when it's going to expire, make sure that the name matches the one that I intended to connect to. So FileMaker ships with a default certificate. As you can imagine, the default certificate means that everyone else with that default certificate has the same private key. That's a problem, because we just talked about how you never, ever give your private key to someone. If you're running with the default certificate, that means everybody else running with the default certificate also has the private key. So yeah, it might protect you a little bit, but not really, because anybody could download FileMaker Server and have a copy of the private key. So you definitely want to get a certificate, and then really the next big challenge is making sure that your users are able to connect to the server by name, by the same name that you used to buy the certificate. We might have time for questions at the end, so sorry, we'll keep going. All right, so SSL has gone through multiple versions, just like lots of things have. Probably the most notable was the compromise of SSL 3. It happened in 2014. When this happened, there was a massive rush. Everybody was patching their servers as fast as possible. It was deprecated the same year that the attack happened because it was so egregious. It was a bad one. TLS 1.0 is what some people upgraded to. And it was pretty good. And actually, there are still some configurations of TS of 1.0 that are probably secure. But there are certain setups that have been determined to be weak. And so just this year, the committees that decide this stuff have deprecated TLS 1.0. So if you have integrations to PayPal or Xero or QuickBooks, a lot of them have been sending out announcements like, no more, you've got to go to TLS 1.1 or 1.2, something like that. FileMaker has been using TLS 1.2 for FileMaker Server ever since, I think, the 1404A patch. So 14, 15, 16, 17 are all using 1.2. As much as it pained some people, a few of those upgrades meant that clients that were behind the upgrade couldn't securely connect. And I don't really fault FileMaker for that at all. It's something that everybody with a web server, like when you had to cross this precipice, it meant people with old browsers couldn't connect to your site anymore. But that's sort of the price of keeping up with the security. All right, so I wish SSL was simpler, but one of the problems with SSL is it's kind of complex. I'm afraid there's not a lot we can do to avoid that. Managing keys and keeping them secure is hard. Getting DNS to work, Bonjour is great, and it works great for your printers, but it's not great for like printing passports. It requires some extra steps to get something like that up and running on your network. There have been vulnerabilities, and so you can't just sort of sit and wait with SSL. You've got to keep upgrading, because sooner or later a smarter mathematician is going to come along and he's going to find some way that's maybe not a complete breach of one of these protocols, but maybe it means that he only has to try, 1/10 as many brute force attacks or something like that, and then we're going to have to upgrade again. Certificate authorities, we really counted on these guys to have our back. It turns out that they weren't always trustworthy. Just in this last year, I won't name the company, but one of the major CAs got kicked out. And that meant a lot of people had to go get new certificates because the ones that they had were deemed no longer valid. So this is a problem with the system. We're kind of counting on companies to do the right thing, and sometimes they don't. Overconfidence, I think, is a big problem with SSL. People think like once they've achieved the green lock that's nirvana, nothing bad could happen. But it really is only protecting a narrow set of things, and it does those very well. I was just at a meetup where a guy demonstrated a live hack on somebody's API during the meetup using a jailbroken iPhone. And so using SSL can provide you a great level of protection, but if your company allows bring your own device or outside clients to connect with machines that you can't be completely sure the state of those computers, the system kind of falls apart. So don't think that you're covered just because you have the green lock. And then revocation. There is a protocol to handle this. So if someone has a rogue employee and they realize they need to pull one of their certificates and get a new one, there's a system for that. It turns out it doesn't really work very well. And a lot of mobile vendors kind of decided it used too much bandwidth, so they just didn't turn it on. So some mobile operating systems actually don't even check revocation. So that's unfortunate, but it's the way it is. So, there's a lot more. I tried to show the SSL protocol exchange in sort of broad strokes. There have actually been some minor improvements to the process that I showed you, but I wanted to kind of communicate the core concepts of what's happening every time you make an SSL connection. So if it's interesting to you and you want to get into the nitty-gritty, there's plenty of material out there you can go dig in. So I'm really surprised that I talked fast enough to get to the end. So we have 3 minutes. If you have a question, could you come up to the microphone? Would you mind and ask it up here? Football, 1. Yeah.
Hey, Chris?
Yeah.
So why do you think FileMaker is doing the Bonjour install? Are they using it for other things besides local host connection? Because it seems to be at cross purposes with the certificate.
Yeah, I'm actually hoping to sit down and maybe talk with some engineers about that at the conference. Bonjour has traditionally been helpful, but FileMaker is definitely strongly encouraging the use of SSL, and it's only going to be a stronger and stronger encouragement to do it. You know, things are on by default now and everything. I think that's the right direction. Unfortunately, Bonjour and secure by default don't jive very well. And so maybe we'll see changes with that in the future. Yeah, go ahead.
If you have a host mismatch, am I right to assume that you're still going to have an encrypted connection? You don't know who it is, who you're talking to.
You don't know who it is, but you are securely communicating with this unknown entity. The problem is that unknown entity might have what we call a man in the middle. So there might be another unknown entity in between you and the unknown entity. And you're securely communicating with the man in the middle.
Got it.
But that doesn't necessarily mean a lot, right?
And then the other question, you all try to get SSL certificates from hosts or from certificate authorities. But there's also a project code called OpenSSL, and I'm sure that you know about this. No?
Do you mean Let's Encrypt?
Yeah.
Yeah. So the security community is actually pretty excited about Let's Encrypt. The people that kind of are on the steering committee of Mozilla and these guys who are deciding who the roots should be. So Let's Encrypt, if you haven't heard of it, is kind of like a grassroots co-op approach to certificates. And since most of the real certificate authorities have completely automated the verification process, it's not really costing them anything. So, you know, why you're giving them money is just because of their reputation. They don't have any cost involved in most of the certificates they issue. So these guys have set up an automated system that will do verification and issue certificates. I think that has a lot of good potential. I'm still kind of waiting to see, you know, do you trust someone if you haven't given them any money? That's sort of a social problem. And then separate from that, right now, there are people who have posted scripts to automate the process of doing Let's Encrypt with FileMaker. So that's kind of exciting. If you run a 24/7 operation, installing a new Let's Encrypt certificate requires basically restarting the server. So if you don't mind kicking people off, it might be a good option for you, or maybe you have a maintenance window that you can do it where it's not a problem for your install base. Maybe we'll see a future version of FileMaker Server that can rotate the certificate without a reboot. That would be great for supporting Let's Encrypt. But Let's Encrypt certificates are short-lived, so they have to be changed more often. With a commercial certificate, you might be able to buy a 2 or 3 year certificate. So in theory, if you're not applying security updates to your operating system or FileMaker, you could have a server that's up for 2 years without interruption. So there's some trade-offs. Yeah, go ahead.
I have run a server behind a VPN or in a VPN for a long time. But now that I'm having to use SSL, it doesn't resolve. It's not really in that location. It can't resolve to a URL or a host name.
Right.
So
in situations like that, you probably, there's multiple ways to attack it. You might be able to use a host in a DMZ that's only routable through VPN. You might be able to use like a split horizon DNS or other things. It's a challenging problem, to be sure. And I think the answer is not, I think depending on your topology, the answer might be different for you.
Right.
We're out of time. Thanks for coming. Please fill out the evaluations.